In this video I'm going to review integration by parts, just to give you an idea of all the different types of integration by parts problems we've done. The first thing we need to recognize is the formula for integration by parts. The integral of some function u times the derivative of some other function dv is equal to u times v minus the integral of v du. So if I'm looking at an integral, something like the integral of x cubed times ln of x dx, I need to identify two things. I need to identify a u, and I need to identify a dv. So a quick rule, and it doesn't always work, but it's a good guide for us right now, to pick who u is we use this acronym called LIE. And this is the order for which we look to who make u. The first thing I look for is some sort of log function. So already in my integral here I see I have a log function, but let's just go through the rest of them. If I don't have a log function, I'm going to next check to see if there's any inverse trig, and then he would be u. If there's no inverse trig, then whatever algebraic term I have, so that's like x squared, some sort of polynomial, that would be what I mean by algebraic. If there's none of that, I'd make it the trig function, and last but not least, if there's really nothing else going on, I would try making it the exponential. The reason why the exponential is the last one there is because when I differentiate e to the x, I still get e to the x. And the whole idea here is that we want to somehow simplify this integral when we get to that integral of v du step. So let's get started. I'm going to give myself a little bit of space to pick a u and to pick a dv. Well, like I said, the first thing I look for is a log function, and there's ln of x right there. So I'm going to make u ln of x, which means that dv is just everything else I have left. So that x cubed and the dx. So if I'm looking at my integration by parts formula, I need to find out who v originally was, and I need to find out who the derivative of u is. So in this case, du is just the derivative of ln of x, which is 1 over x dx. And to get back up to v from dv, I'm going to take the antiderivative. Right, so I'm going in the opposite direction. I'm going to use the reverse power rule, add 1 to the exponent, and divide by it. Now I could always check that I did this correctly by differentiating. Right, and the derivative of x to the fourth over 4, if I bring down the 4 and subtract 1 from the exponent, would just get me x cubed. So that's okay there. So now I'm going to start making my substitutions into this formula right here. So this integral is equal to u, which in our case is ln of x, times v, which we have as x to the fourth over 4, minus the integral of v, x to the fourth over 4, du, which is 1 over x dx. Alright, so I'm going to zoom in a little bit just so we can analyze this a little bit further. The whole idea of integration by parts is that the integral we end up with should be easier to deal with. So if I'm looking here algebraically, I could simplify this a little bit, where if I multiply it, x to the fourth over 4x to the first just simplifies to 1/4 x cubed if I subtract those exponents because I'm dividing. Now, I could write this as the integral of 1/4 x cubed dx, but I always like to put my constants on the outside of the integral just so there's a little bit less to look at there. So really, the only integral I still need to find is the integral of x cubed dx, which we already found when we took the antiderivative of dv. So I know that just turns into x to the fourth over 4, but what I need to remember is my constant of integration here, since this is my last step in my integration problem. So I could write it as negative 1/4 times x to the fourth over 4, but if I multiply that to one fraction, it'll just be minus x to the fourth over 16, and I got all that business in the front to bring down. ln of x times x to the fourth over 4. Now I know some of the problems we've done have been a little intensive, but you'll know when you're done when you're able to take the integral of what you have on the right hand side there. So this would be my final step in finding the antiderivative of x cubed ln of x dx. And if you're not sure, you could always differentiate, right? You could use the product rule here, use the power rule there, and just make sure you get the same thing back. Number 2, find the integral of x times sine of x dx. Well, here, I can say that u is x, that's my algebraic term, and du would then be dx. And the only thing I have left would be sine of x dx. and the antiderivative of sine of x dx is just negative cosine of x. That's just something you need to memorize, and you can check yourself by differentiating. Because remember, the antiderivative of the regular derivative of cosine is just negative sine. So if I want to get out positive sine, I'd have to negate that. That's the thought process there. Always check yourself by differentiating. So I'm going to start substituting into the integration by parts formula. U times v minus the integral of v, negative cos x, du, which in this case is just dx. So this is looking pretty good. There's not a lot going on here. I see two negatives, and if I pull that negative on the outside, I can just make it positive. And the whole idea is that this integral we end up with should be easier to deal with. So the integral of cosine of x is just positive sine of x, and I'm going to add my constant of integration there. So not a lot going on though. There's just x to the first power and sine of x, no constants being multiplied to x. So let's try one more example where the functions are a little bit nicer, and then we'll go to some lengthier ones. For number 3, find the integral of 5x minus 9 times e to the x dx. Again, I want to pick a u, and I want to pick a dv. Now, exponentials are always my last choice for who u is, so I'm going to make u that linear term, that 5x minus 9. I'll call that my algebraic term, which means dv is just e to the x dx. So the derivative of 5x minus 9 is just 5 dx. And let's see right here. The antiderivative of e to the x is just e to the x, because if I differentiate, I still get e to the x, so that's not going to change there. Again, I'm going to start making some substitutions. U times v minus the integral of v du. This is just a constant times e to the x. I know how to deal with this. This would be the same thing as writing minus 5 times the integral of e to the x dx, because I could just pull it out as a constant being multiplied to my exponential there. And we already know what the antiderivative of e to the x is. We've done that already. That's just e to the x. And I'm just going to add a constant of integration because I've finished my integration problem here. So my final answer is just 5x minus 9 times e to the x minus 5 e to the x plus c. Now we have a couple of constants we need to deal with. But this looks pretty similar to x times sine of x, and you'll notice structurally it really is. Again, I'm going to make ux my algebraic term, and I'm going to make dv cosine of 3x dx. Now, du is pretty simple to solve, right? And that's just dx. The real question is, how do I take the antiderivative of cosine of 3x? Now, what we're going to end up with is, if there's a constant being multiplied to x, I could just multiply by the reciprocal and ask myself, what's the antiderivative of cosine? It's just positive sine. And if you don't believe me, we actually derived this rule by doing a little bit of u substitution. So you would never have to do this all the way out on a test or something, but if you forget, the reason this works is because I don't know how to deal with cosine of 3x, but I could do a u substitution real quick to make u equal to 3x. So du is equal to 3 dx, and the only thing I need to get rid of in my integral still is that dx there. So I'm going to divide out 3 to find the 1/3 du is equal to dx. So this integral now becomes 1/3 times cosine of u du, and if I take the antiderivative, that's 1/3 sine of u, which is just 3x, plus c. So that's where we get that 1/3 sine of 3x from. You don't need to know the derivation of that. It's a lot easier to just memorize the rule where if there's a constant being multiplied to x, multiply by the reciprocal. All right, so I'm going to continue with my integration by parts. U times v minus the integral of v sine of 3x du. Now, this is the same issue, right? There's a sine and a constant being multiplied to it. So if I take the antiderivative of sine is negative cosine. So I'm just going to make that a plus since I know it's going to be a double negative. I'll bring down the 1/3. And remember, the antiderivative of sine of 3x is negative 1/3 cosine of 3x plus c. If you can see that you're going to pull another 1/3 out, you can multiply those already just to make it 1/9. And I'm just going to bring down all that stuff to begin with. So my final answer, again, looks very similar to the second one we did, only now there's a couple of constants. That's it. X times 1/3 sine of 3x plus 1/9 cos of 3x plus c. So again, that negative became a positive because sine is going to turn into negative cosine. Now there's some other u substitution problems that we could do, something like when we're working with inverse trig. Now, it doesn't really look like there's a lot of candidates for u here. I know dv should just be dx because that's the only derivative I have of anything. And I'm just going to make u the inverse cos function. So by that logic, if u is arc cos or inverse cos, the derivative of that, that's just something you need to memorize, is negative 1 over radical 1 minus x squared dx. And if dv is dx, then the antiderivative of dx is just x. So this might get a little chunky when we plug in. Let's see what happens. U times v minus the integral of v du. All right, couple of things I notice here. There's a negative 1 out in front here that I'm going to pull out just to make my life easier, to make that a plus on the outside. And the whole idea of integration by parts is that the integral you end up with should be easier to deal with. So there's no, special antiderivative here. There's no reverse power rule. So the next thing I try is a u substitution. And that 1 minus x squared, I really don't know what to do with. But as I'm thinking in my head, if I make u equal to 1 minus x squared and take the derivative to get negative 2x dx, I know I end up with some x to the first term, and I'm trying to get rid of an x to the first. So that's how I can see in my head already that this is probably going to be a u substitution problem. If I divide out the negative 2, I find that negative 1/2 du is equal to x dx. And that's precisely what I still need to get rid of in this integral here. So this integral now becomes, if I pull out the negative 1/2, the integral of, well, 1 over radical u, and then x dx I could just replace with du. If you're not sure how to deal with this yet, try rewriting it. I could rewrite radical u as u to the 1/2, but again, it's in the denominator, so it doesn't help me that much. If I bring it up to the numerator, remember, I just need to make the exponent negative. Now I know how to deal with this. This is just a reverse power rule. Add 1 to the exponent, so negative 1/2 plus 1 is positive 1/2, and divide by it. But dividing by 1/2 is, it leaves me with a complex fraction. So I'm just going to very quickly multiply by the reciprocal instead, which is equivalent. And that works out because if I'm multiplying by negative 1/2 here, that reduces to just negative 1. So really this entire integral is just negative u to the 1/2 plus c. But remember, we made u 1 minus x squared all the way up there, so that would just be negative 1 minus x squared to the 1/2 plus c. And I've still got the first part of it, don't forget, x times cos inverse of x. So you could leave your answer just like this, or if you wanted to rewrite the 1/2 exponent as a radical, just because usually that's more useful to us, you could do that. And both of those are equivalent, as long as you remember to substitute back in for u at the end there. Let's try one more example. Let's take a look at number 6, x squared times e to the negative 3x dx. This is what I call a worst case scenario problem, because there's some sort of coefficient in front of the x for the exponential, and instead of just being a linear term, there's an x squared. So this might be one of those double voodoo problems. I'm still going to make u my algebraic term, x squared. Let me use black here. And I'm going to make dv e to the negative 3x dx. All right, well, du is 2x dx. And v, if I take the antiderivative of e to the negative 3x, I can multiply by the reciprocal of that constant, negative 1/3. And the antiderivative of e to the something is still e to the something. So these are the pieces I'm going to work with and start plugging in with. So u times v minus the integral of v du. Alright, so this part I know I'm just going to keep bringing down, so I'm not even going to look at them for now. I'm going to ask myself, how can I deal with this integral that I have left over with here? Well, notice you've got two constants. I've got a negative 1/3, and I've got a positive 2. I could multiply those to pull them out in front to just make it positive 2/3, right, because there's already a negative there, times the integral of e to the negative 3x times x dx. And you might even know what's going to happen here, but there's no reverse power rule. I'm multiplying two different functions of x, one where it's an exponential, one where it's an algebraic term. My only option here is to do another voodoo. You could try to do u substitution, but because these are the same powers of x, you're not going to get anywhere. So I'll make u, again, my algebraic term, and I'll make dv my exponential. Negative 3x dx. Now, this isn't going to be that bad because we know the derivative of x is just 1 dx, and the antiderivative of e to the negative 3x, we've already found that. So we know that's negative 1/3 e to the negative 3x. So if I start substituting in again, this integral is just going to become u times v, negative 1/3 e to the negative 3x, minus the integral of v, negative 1/3 e to the negative 3x, du, which is just dx. So I've actually solved my problem because there's no other x in that last integral there. The only thing you need to worry about is that, remember, we're multiplying this whole thing by 2/3 on the outside. All right, well, the question you should ask yourself is, do I know how to work with this integral now? Well, one thing I could do is I could pull out that negative 1/3 to make it a positive 1/3 on the outside. And I know what the antiderivative of e to the negative 3x is. We've already done that twice. Right, that's just going to be negative 1/3 e to the negative 3x. So when I multiply those constants, I could just make that negative 1/9 e to the negative 3x plus c. And remember, there's still this x times negative 1/3 e to the negative 3x. And I'm still multiplying all this by 2/3, which is good, but don't forget that I also have all this business right here, that x squared times negative 1/3 e to the negative 3x that I'm adding to that. So notice there's no more integral sign, and this is my final answer here. I'm not going to ask you to simplify any further. You can if you want to. You can multiply out all your coefficients. You could bring out the negative 1/3 x squared e to the negative 3x plus, if I multiply that 2/3 in there, that's going to be a minus 2/9 times x e to the negative 3x, and then minus 2 over 3 times 9 is 27 e to the negative 3x, plus, when I multiply 2/3 to some constant, I get another constant. So both of these forms are equally correct. It's up to you if you want to simplify. As long as you're careful with your constants, you'll be fine.